recap, in case you forgot, we started looking at viscoelastic models. So these are the models which have an elastic part, which is spring, and they have a viscous part, which is the dash part. And we started with this Maxwell model, where the spring and dash part are in series. And we looked into the creep behavior. And we saw that the creep behavior looks something like that. If you hold the stress constant, then you have immediate instantaneous elastic strain, then viscous strain. The moment you remove the stress, it goes down as much as it has elongated in the beginning and it stays there. We have permanent deformation. This was the creep. And this is how it looks like nicely. And we also introduced something else, relaxation. That is when we keep the strength constant, and it turns out that viscoelastic materials relax themselves. The stress becomes smaller. Look at the arrows. They are becoming smaller. So if we hold the strength constant, we saw that the relaxation means that the stress starts at E epsilon 0 being the constant strain, and it relaxes itself exponentially. Now we want to do a few examples on that. The first example is here. Let me open the other file. You have the example. So we have a glass cylinder at very high temperatures. So that's why it behaves viscoelastically. Look at the temperature, 450 degrees Celsius. And we hold the load constant. We want to see what will be the strain after 100 hours. So I gave it away that this is a creep problem. We have to first recognize the stress is constant. We want to see how much strain we'll have over time. Now, we have to solve it. In this case, I'm telling you that we model the behavior of glass with Maxwell model. I'm giving you this information. Now, let's calculate the strain. We want to see how much strain we have after 100 hours. I suggest that you start with drawing the model, and then let's draw a strain versus time. So the model is a Maxwell model. Pay attention to the terminology I use. This is the model. The parameters are E, elastic modulus, lambda, viscosity. Right? Now, at time 0, so this is time, this is a stress. At time 0, I apply some stress, and I hold it for 100 hours. How would the strain versus time diagram look like? And then we have to calculate it. That's the time. Well, this depends. So let's draw this strain versus time diagram. Let me see. Benefit of the small class is that I can check on everyone. How would it look like? That's exactly why I want you to do that. Pay attention, we are not unloading. I didn't talk about unloading. Let me draw this differently. I want to have them. So here is sigma 0, and I hold it for 100 hours. So the strain, in the beginning, you are going to have instantaneous elastic strain, and then afterwards, the dashpot, and I didn't mean that I don't unload here, it's just, I know only up to 100 hours. So it's not unloading, it's more like that. This is how it looks like. It's super important that you can understand, or you can go from a stress to a strain diagrams. And what is this, a slope? This is sigma 0 over lambda. And the elastic strain is sigma 0 over E. So we have the strain is a combination of elastic strain plus viscous strain. So E for elastic and V for viscous. The elastic strain is sigma 0 over E. And the viscous strain, since sigma 0 is constant, I'm holding this 100 Newton force, would be sigma 0 lambda times T. You can see the figure. So if I hold it longer, it becomes larger and larger. It scales with T. Now, try to calculate the two parts separately, meaning that write it like this, but calculate each part separately. Of course, first you have to calculate sigma 0, and then get the numbers. I have to see 3 correct answers. One correct answer. And you need to compare the elastic and viscous deformation to get a sense. So I think everyone is doing good. I just write it quietly. You can just check by looking. Pay attention, there is no unit for a strain, right? Check your numbers. So this is basically first calculating sigma 0. You have to be careful about units. And if you substitute for the two parts, we have 21.23 microstrain, that's micro, elastic, and 0.19 viscous. So what we see is that the viscous deformation is much larger than elastic. This means much larger, orders of magnitude larger. So first you apply the load, you have elastic deformation just a tiny bit, and then as you hold the load, the same load, you are not changing the load. For a long period of time, it's actually not very long, 100 hours, how long is time? How many hours? 48? 48? 46? So it's a little bit more. And then it deforms a lot more. So we see that the viscous deformation is a lot larger. The next example, does everyone have everything on the board? I like a small class, it's great. Now, this problem, we have the same material, but now we stretch it to a certain strain, which is 50 microstrain, that is 50 times 10 to the minus 6. That's what it means. And now we want to see two things. One, what is the initial stress? And then what happens after 10 seconds? So let's look at the first part. So this is not a creep problem anymore. We keep the strength constant, and we want to see what happens with stress. So it is a relaxation problem. I suggest that you draw the relaxation curve for Maxwell, put the formula, everything probably comes from the notes, and then everything becomes a lot more clear. Go back to the notes a few pages before. Draw the diagram. So this is the relaxation diagram, in case you are still looking for it. Try it once for yourself. So you hold the strain constant at 50 microstrain, and what happens is that the stress starts from somewhere and then it exponentially goes down. So it starts from here. And goes exponentially down. When you first apply the strain, how much is the stress? Sigma 0. Exactly, it is E times epsilon 0. Because the moment you apply the stress, the strain, all the strain is going to be carried by the friction. Because it deforms immediately. So the initial stress is E epsilon 0. And this is what it is asked in the beginning. So at t equal to 0, sigma is sigma 0, and it is E epsilon 0. E is 15 E9, and epsilon 0 is 50 E minus 6. So it is 750 E3 Pascal, or better say 750 kilopascal. How about after 10 seconds? After 10 seconds, you can see that for this material, if you have 10 seconds later, the stress is going to be smaller. And the relationship, it is going to be smaller according to this exponential decay. So all we need to do is to say, okay, so after 10 seconds, t is 10 seconds, so sigma is sigma 0 E minus E over lambda t. You already know that this is 750, and we just substitute. This is Pascal second, and that's second, so everything is good. I think you would get something about 584. So if I ask you at some other time, you see that if it is after 10 seconds, it becomes smaller and smaller. Now, I told you viscoelastic models are like Lego. So we have a spring model and a viscous model, and we try to arrange them in different ways. We saw how it looks like if we put them in series. Now the natural thing is to look what happens if we put them parallel. Is everyone done with writing? Few people are still writing. So the next model is called Kelvin model, and we put the dashpot and a spring in parallel, and we want to see what happens. So, instead of putting them in series, they're in parallel like that. And we look at the creep behavior, meaning that the stress is constant. And we see that this model predicts a retarded deformation behavior. It means that the deformation doesn't occur immediately, it occurs after a certain time. How does it look like? Maybe I should go back here. Here you can see that sigma is equal to sigma E plus sigma V. The force that you apply is going to be carried by a spring plus dashpot. And if you want to look at creep, we want to see what happens if this is constant. Now, we know how to relate epsilon and sigma for elastic and viscous material. For elastic, sigma is E epsilon. Correct? For dashpot, it is lambda d epsilon v dt. And now we know that the summation is constant. But these are parallel. It means that the deformation has to be the same. So we can just, instead of saying epsilon E and epsilon V, we can just replace it by epsilon. And I write it a little bit nicely, divide both sides by E. So this is a differential equation again in epsilon. We want to see what would be the epsilon if we keep the stress constant. This is a differential equation. And the solution to this differential equation is basically what you have here. So when we apply the stress, the spring wants to immediately deform, but the dashpot prevents it from immediately deforming. So it causes a retarded deformation. What I want you guys to do is try to plot this response. Now we know how it looks like here. So here is the Kelvin model. Here is the stress my favorite stress diagram. First, there is no stress, then I apply a constant stress, and then I remove it. And the equation, I just gave it to you. So the differential equation, it gives an answer which looks like that. Check everything is good. Now let's first just concentrate. If it is 0, and then when you load it, what happens? Draw this graph, it's an equation. How do you think it will look like? So you need to think about You should think about the things I told you. So the dashpot and the spring, they have to deform together. They have to. And then sigma 0 is sigma E plus sigma V. But this is important. And here is the equation that we got by solving for that. But the key, this is when you start to put the stress. So if there is no stress, everything is good.
Oh, okay.
That is it. Not everyone is sensitive. You have the equation. Let's see if you want to solve this. For that stress. So first there is no stress, and then I apply sigma. How does this look like? It's very useful to think at time 0 and at very long time, what would be the answer? And then you draw it. Absolutely correct answer. So in the beginning, when there is no stress, the strain is 0, right? And then you start putting the stress because there is no stress here, so the strain will be 0 in the very beginning. When you apply the stress, then this equation comes into play. And if you think in the very beginning it's 0, And then it's going to increase, and if you wait long enough, if you really wait a long time, when t becomes very, very large, this becomes 0. So it approaches sigma 0 over e at a very long time. But we haven't been patient enough. We have abrupted the loading at t0. Let me use another color. So the moment you abrupt the loading, it's going to relax exponentially. So if you start from some epsilon max here, you are going to relax and this is basically this t here. I call it t max. It's going to exponentially relax. And eventually it's going to completely recover, because remember, the spring and dashboard, they have to have the same strength. If you wait long enough, the spring wants to bring everything back to 0. So you are going to go back to 0. I have a more beautiful plot which looks like that. This is important that you understand what happened. So it approaches at a very long time. This infinity sign means if you are very patient, the sigma 0 over e. But if you unload, it's going to go back exponentially. Again, so if you start from here, it's going to go back, and this is t max. What is important is that you remember that it's going to go back exponentially. And if you want to put it in English words, you have delayed deformation or retarded deformation, sometimes people say, but you have full recovery. Why? So you don't have deformation right away. It takes some time for it to develop, but eventually everything is going to go back. That's Kelvin. No questions about this? Here? I told you this is a Lego game. So, and if you look at this, this doesn't look like the creep behavior I showed you in the graph. So it's not good enough. We need better model. What do we do? The next model, we take the Kelvin model, we put it in series with the spring. Now, I challenge you to draw the response to that. In terms of equations, these are in series, so it would be epsilon would be the epsilon from this spring plus the epsilon from the Kelvin model. So it's just summation of the two. So that's the spring, and this is the Kelvin. And I can sum them up because they are in series. So nothing new. How many model parameters do we have here? 3. What are those? Exactly. terminology is important. Make sure when I ask for model parameters, you know what I'm talking about. So we kind of make up some models. We try to analyze the response, and we want to see what models best describe the materials in those dimensions. So this is how it works. We have 3 material models now, E1, E2, and lambda. And this is how it looks like. Now, of course, as you may guess, I want you to draw it. Here is the solid model. I forgot the name. So it's called solid model. Now, if you have this kind of a stress, what would the response be? Try to put the numbers, like how much is there. One correct answer. Looks good. Make sure that you decide whether you have complete recovery or not. To be clear. Here we have E1 and E2. So just writing E, it won't be good enough. It looks great. This is how it looks like, right? In the beginning, you have sigma 0 over E1, and then you are going to have this which at some point, if you don't unload, it's going to be sigma 0 E1 plus sigma 0 E2. But if you unload, you get exactly sigma 0 over E1 down, and eventually it's going to go to 0. So don't make this to go to 0 like that, because that's not the case. It's exponentially dependent. So it's time dependent, but we have total recovery. This is important. It has to be intuitive now. You should kind of feel it and believe it. You have put a spring here and Kelvin. They both bring back things to 0. So this goes back to 0. In the beginning, always the springs are going to be linear elastic. It's going to be immediate, instantaneous deformation upward. And as you can guess, we make things a little bit more complicated because it's still not like the field curves that we measure in the lab. So we need to add more complexity. What do we do? Next time, we put a Kelvin and a Maxwell model into it. It's on the dashboard. And we call this Berger's model. This is the last model I teach you. There are tons of models, but the fourth and the last one is when we have a Kelvin in series with a Maxwell. And this turns out to be a pretty good model. So Maxwell, Kelvin in series. That's why you sum them up. How many model parameters we have? Someone else? 4, thank you. And these are? Thank you. So in the homework that I already uploaded and it's due next week, you'll see some examples where you have to recover and after your model parameters. I want you to not to be confused. What I want is what are then E1, E2, lambda 1 model, depending on the model. Okay, get busy. Try to see how the model would. Yes, I know. It's the last one. Come on. You can do it. I actually models can be linear, non-linear, elastic. So make sure that it's clear.
What? Oh, so in the so let me put this before the computer.
These are actually three different colors. It doesn't show up. So in the beginning you have sigma 0 over E1, and then you have this sharp increase. And then it's kind of sharp increase and linear. So you have kind of the dashboard part, and you have the Kelvin model both together here. And when you remove, of course, sigma 0 over E1 immediately recovers, but then the Kelvin model also eventually recovers. But at the end, you have permanent deformation as much as the deformation of the dashboard. And if you remember the creep curves that I showed you earlier in the beginning to motivate everything, just want to show you because you see that this model is pretty good, right? It's becoming very close to the material behavior that we record in the lab. So it can be used to describe the behavior of the material we want to describe in the lab. So that's why this is a good model. So we have this part and this part are exactly equal. And then you have this part, which is like sharp increase. And then you have kind of, it turns into a line. It's important that you recognize that this one will be left with permanent deformation, right? Unlike the solid model, where everything was going back to zero. You have this non-linearity, but obviously this is not linear. And you have a part of the deformation is instantaneous, but a large part of it is not. Now, you saw that the laptop is also it's going to go out of power. Next week, the bad news is that I'm going to a conference, so I won't be here on Monday and Wednesday. But I'm going to post the lectures on YouTube. 2 50-minute lectures. So it's a visual class. I don't know what else I could do. On Friday, very important. I'm going to send an email too, but on Friday, the 23rd, the TA she will hold the class, and you have a homework Yeah, and the TA will send an email with her office hours next week, so if you have any questions, you can go to her or email me. Well, have a nice fun weekend.